You ever wonder how all this super complex software that pretty much runs our world is, well, built? A massive part of the answer is something called object-oriented programming, or OOP for short. And let me tell you, it's not just some fancy coding style, it's a total game changer in how we even think about solving problems. So let's dive in and really get what it's all about.
All right, let's kick things off with a little puzzle. Think about your car, your phone, and your bank account. What on earth could those three things possibly have in common? I know, it sounds like a totally random list, right? But trust me, the answer is the key to, well, everything we're about to talk about.
The answer is, in the world of programming, we can think of all of them as objects. And that right there is the huge idea behind OOP. It's all about taking how we already see the world, as a collection of distinct things, and bringing that exact same logic right into our code. Pretty smart, huh?
Okay, so let's really dig into this foundational idea of OOP. This whole concept that everything, and I mean everything, can be looked at as an object. So what does that actually mean for something to be an object in code? Well, think of it like a neat little self-contained package. And inside this package, it bundles two things together. First, it's data. We call these attributes. And second, the functions that can do stuff with that data, which we call operations.
Let's make this super clear with our car example. The car's attributes? That's what it is. Things like its manufacturer, the model, its color, the year it was made. And its operations? Well, that's what it can do. Start, drive, park, stop. See? By grouping all of that together, we've created a car object that's basically a digital twin of a real car. Okay, that makes sense. We get what an object is, but hang on. If you're a car company and you need to build thousands of cars, you're not going to design each one from scratch, right? Of course not. You'd use a blueprint. And guess what? That's exactly how it works in programming.
In the world of OOP, that blueprint has a special name. It's called a class. A class is the master template. It's what defines all the possible attributes and operations for any object made from it. So every single object we create is what we call an instance. It's just a specific, unique copy made from that class blueprint.
And this car factory analogy just nails it. Think about it. The master engineering diagram for, say, a Tesla Model 3. That's the class. It's the blueprint. But each individual car that actually rolls off the assembly line, the physical thing with its own unique VIN number that you can go and drive, that's the object. It's one specific instance that was built using that blueprint.
All right, so now we've got objects and classes down. Let's get to the really cool part. The 4 powerful principles that make OOP so effective. I like to think of them as OOP's 4 superpowers.
And here they are: abstraction, encapsulation, inheritance, and polymorphism. Don't worry, they might sound a little intimidating, but the ideas behind them are actually pretty intuitive. You can even remember them with the acronym AEIP. Let's break down what each one does, and more importantly, why you should care.
First up, we've got abstraction. And honestly, this is all about one thing: hiding complexity. The whole idea is to show only the essential, necessary features of an object to the outside world, while all the complicated, messy inner workings are tucked away, hidden from view. Simple on the outside, complex on the inside.
I mean, look at your phone. It's the perfect example. You tap a single button to send a message and poof, it's sent. You have no idea about the insane amount of stuff happening behind the scenes, the complex circuitry, the radio signals, the data protocols, and you don't need to. That is abstraction in action. It just simplifies everything for you, the user.
Next up is encapsulation. The name kind of gives it away, right? It's like putting things in a capsule. This is the principle of wrapping up an object's data and the functions that work on that data all together into a single protected unit. And this is so important because it protects the data from being messed with from the outside. It prevents accidental changes, which, let me tell you, is a huge source of bugs in software.
A car's battery pack is a fantastic real-world example of this. It's the sealed, self-contained unit. You interact with it safely through one specific point, the charging port. You can't just, crack it open and start poking at the individual cells inside, right? That would be a disaster. In the same way, encapsulation protects the internal data of an object, making your code way safer and a whole lot easier to manage.
Our third superpower is inheritance, and this one is a massive deal for efficiency. It's all about reusing code. Inheritance lets you create a brand new class that's based on an existing one. And when you do that, the new class automatically gets, or inherits, all the properties and abilities of the parent class. It's like passing down traits in a family.
So check out this classic example of an inheritance hierarchy. You start at the top with a very general class like vehicle. Then you can create more specific classes that inherit from it, like land vehicle and air vehicle. Then you can get even more specific. From land vehicle, you can create a car class and a bus class. Each new level down inherits everything from the level above it. This creates this beautifully clear and organized structure. And here's the magic. You write the basic vehicle code once, and everything underneath it just gets to use it for free. That's efficiency.
And last but not least, our fourth superpower, polymorphism. It's a big word, but it literally just means many forms. Think of it like a shapeshifter. In programming, it's the ability for one single action or command to do different things depending on what kind of object you're using it on.
Here's a super simple example you already know, the plus symbol. If you use it with numbers, like 5 plus 5, what happens? It does addition, and you get 10. But what if you use that exact same symbol with text, which we call strings, like hello plus world? It doesn't try to add them, it joins them together to make hello world. See? Same symbol, completely different behavior based on the context. That is polymorphism.
So you might be thinking, why was this whole object-oriented thing such a revolutionary idea? I mean, what were we doing before? To really get that, we need to take a quick look at the old way of doing things versus the new way.
So before OP came along, the main style was procedural programming, and it was all about doing things. It focused on functions, or the verbs. The problem was, the data, the nouns, was just sort of out in the open. It could be accessed and changed from anywhere in the program. In a small project, maybe that's okay. But in a big one, it could turn into a tangled mess, what programmers call spaghetti code. OP flipped that completely on its head. It said, let's focus on the data first, the nouns, and keep it safe inside our objects.
And you know, this shift in thinking wasn't just some boring academic exercise. It had huge real-world consequences. In fact, it's the very foundation for a ton of the technology that you and I rely on, like every single day.
I mean, seriously, the applications are just everywhere. Think about an AI system that needs to understand a person or a vehicle as a complex thing with its own data and behaviors. That's OOP. What about a database that needs to manage your bank account as a secure, self-contained little package? Yep, that's OOP too. It gives us the structure we need to build the massive, complex systems that power our modern world.
Look, if you walk away with just one thing today, let it be this. OOP is all about building these self-contained, self-sufficient objects. That's the core idea. And this way of thinking leads to code that's more organized, way more secure, and much easier to scale up. It's how we build really, really big things without them just collapsing under their own weight.
So there you have it, a whirlwind tour of object-oriented programming. But now it's your turn. Just look around you right now. What's the first real-world object you can see that you would try to design in code? A coffee mug? A laptop? A pet? The possibilities are literally endless. Thanks for sticking with me.